Our everyday intuition about how magnets push and pull completely falls apart when we scale down to the level of atoms and electrons. In classical electromagnetism, there is a hard, absolute rule. For a magnetic field to exert a force on a charged particle, that particle must be moving. This is the Lorentz force equation. It defines exactly how a magnetic field pushes on a moving charge. Because of the cross product, if the velocity is zero, the entire right side drops to zero. A stationary charge feels no push from a magnetic field. Yet macroscopic materials sitting perfectly still on a table will suddenly snap and jump toward a strong magnet. Pour liquid oxygen between the poles of a magnet, and it will physically bridge the gap, held there against gravity. The oxygen molecules have no bulk velocity, yet their unpaired electrons create an immediate attraction, known as paramagnetism. Since objects at rest react to magnetic fields, the Lorentz force cannot explain the full scope of magnetism. A hidden interaction framework must operate beneath the classical laws. At the quantum scale, particles possess internal properties that have no direct equivalent in classical physics, such as intrinsic spin and orbital angular momentum. Because these particles carry an electric charge, their quantum properties generate localized magnetic moments. These act like microscopic bar magnets that interact directly with an external field, independent of the particle's velocity. We represent this interaction through the magnetic interaction Hamiltonian, which defines the exact energy of the system. This total magnetic moment vector is built from two distinct parts, the electron's orbital contribution and its intrinsic spin. The dot product in this Hamiltonian means that the energy of the particle is determined by spatial alignment. A magnetic field modifies the internal energy states based on whether its magnetic moment points with or against the external field. This results in the Zeeman effect. A single energy level splits into multiple discrete levels the moment a magnetic field is introduced. This splitting bridges the quantum world to our own. The lower energy spin states naturally become more populated, and that unequal distribution causes the bulk paramagnetic alignment we see in materials like oxygen. However, a subtle problem remains. While this Hamiltonian explains how energy splits, it still treats the classical B field as the primary actor in the quantum system. To integrate magnetism with quantum mechanics, we must eventually look past the B field and identify the more fundamental variable. We can view the magnetic field as a secondary derivative of a deeper spatial field known as the vector potential. Mathematically, the B field is defined strictly as the curl of this vector potential, represented by the letter A. Classical physics often treats the vector potential as a purely mathematical tool, used only to simplify field calculations. Quantum mechanics reverses this hierarchy. In the fundamental equations of motion, the vector potential replaces the B field entirely. This is the full quantum Hamiltonian for a charged particle moving through an electromagnetic field. This specific substitution is called minimal coupling. Here, the vector potential embeds itself directly into the kinetic momentum operator. Because it is coupled to the momentum operator, the vector potential possesses the ability to directly alter the phase of the quantum wave function. Under this quantum framework, the vector potential directly rewrites the particle's underlying probability wave, replacing the classical concept of an invisible force. A definitive stress test exists to determine if the vector potential is an observable physical entity. We look for a measurable effect in a region where the magnetic field is zero, but the vector potential is not. Theoretical physicist David Bohm formalized this thought experiment to challenge the limits of classical field theory. The setup involves a coherent electron beam, split to travel down two separate paths around a perfectly shielded, localized magnetic solenoid. The shielding creates a strict condition. Along the paths the electrons travel, the magnetic field is absolutely zero. Even with the B field confined inside the cylinder, the vector potential extends outward. As the electrons pass by, the vector potential couples to them, asymmetrically shifting their wave function phases. When the two beams recombine at the detector, their interference pattern has measurably shifted compared to when the solenoid is turned off. The Aharonov-Bohm effect demonstrates that the vector potential is a physical entity, altering quantum reality even in the absence of a magnetic field. Relying on the vector potential introduces a mathematical paradox. The field itself is non-unique. This is gauge freedom. It means the vector potential can be changed by adding the gradient of an arbitrary scalar field, represented here by chi. Taking the curl of this altered vector potential cancels out that arbitrary addition, yielding the exact same magnetic field. This suggests a logical crisis. If the vector potential alters the wave function physically, but we change it arbitrarily through math, the results appear inconsistent. This is solved by recognizing that gauge transformations change the mathematical representation, not the objective physical reality. To preserve the physics, quantum mechanics requires gauge invariance, a mechanism that ensures measurable reality ignores these arbitrary mathematical shifts. In gauge invariance, whenever the vector potential transforms, the wave function's phase transforms in perfect lockstep to compensate. This equation shows the phase transformation required to perfectly balance the arbitrary gauge shift. This resolves the paradox because physical properties are derived from probability density, not the absolute phase. When calculating density, that arbitrary gauge phase factor cancels out, leaving measurable physics unchanged. This theoretical mandate governs applied computational chemistry and physics. When calculating molecular magnetic properties, chemists must explicitly build gauge invariance into their software to avoid contradictory results. Researchers use gauge-including atomic orbitals, or London orbitals, to enforce gauge consistency across complex molecular geometries. Without these rigorous constraints, simulations of aromatic ring currents in molecules like benzene would yield physically impossible gauge-dependent errors. Macroscopic magnetism serves as the physical evidence of these meticulously balanced gauge-invariant quantum phase shifts, all orchestrated by the vector potential.